So remember, the changes in membrane potential are population behavior. The depolarization correlates mostly with an increase in sodium permeability, and repolarization correlates mostly with an increase in potassium permeability. We're going to talk about both of these things, but we'll talk first about the sodium side of the equation because that's responsible for the depolarization. So voltage-gated sodium channels are what causes it, and they're found all over the axon hillock and all throughout the axon. Now, like the name suggests, this is a family of voltage-gated channels that are selective for sodium, and they're gated, opened or closed, by changes in membrane potential. Voltage-gated sodium channels are going to allow sodium to enter the cell because channels do passive transport, and so sodium follows its concentration gradient. Remember, it's higher outside. But as the sodium comes in, it brings with it its positive charge, and that creates depolarization. Now, you've heard me use a door analogy a couple of times when talking about ion channels, and that works pretty well. With this specific channel, when the door is closed, we say the channel's in a closed state, and sodium ions can't enter the cell. There's no pore. When the channel's in an open or active state, the door is open, now sodium ions can flow into the cell because the pore has been created. But unfortunately, there's one complication with the voltage-gated sodium channel, which is that it actually has three states. In addition to being open or closed, it can also be in an inactive state. Now, one way that we can think about this conceptually is to imagine that voltage-gated sodium channels actually have two doors, sort of like how your house might have a screen door and a door for security. In order for someone to enter your house, both the screen door and the security door have to be open. If either door is closed, then nobody can come inside. So this third inactivation state is kind of like a situation where one door is open, but the other door is still closed. And that means that in this inactivation state, sodium ions can't enter the cell because no pore has been created. To try to help us understand this a little bit better, here's another diagram which is representing a single voltage-gated sodium channel up at the top, and we're correlating the changes that it makes to membrane potential down at the bottom. So in this diagram, the two doors on the channel are represented a little bit more clearly. One door is known as the activation gate, and it's represented by the yellow bar at the center of the channel. The second door is known as the inactivation gate, and that's the ball and chain looking structure down at the bottom. So from this first part of the diagram, we can see that at resting membrane potential, this voltage-gated sodium channel is in a closed state. Its activation gate is closed and its inactivation gate is open. So again, with this configuration, we say that it's closed, and this happens at resting membrane potential. Now, the activation gate is voltage sensitive. So in this diagram, that's represented by the plus and minus signs that are attached to the activation gate. Keep in mind that this whole structure is a protein. So in reality, the voltage sensitive region is most likely a sequence of charged amino acids. So when that depolarizing stimulus that we've just finished talking about before comes, the inside of the membrane becomes more positive. And this voltage sensor is going to experience electrostatic interactions, and it'll start to reposition itself within the membrane. As it does this, it pulls open the activation gate. So this second part of the figure is really a snapshot of an in-progress view trying to show us that happening. You can see the activation gate is partially open. And it doesn't become fully open until membrane potential reaches what's known as threshold, which is represented in this diagram as the dotted line at minus 55 millivolts. If the depolarizing stimulus isn't strong enough to move membrane potential all the way to minus 55 from rest, then the action potential doesn't fire because the activation gate doesn't open and sodium permeability doesn't change until the channel's open. But in this example, it does reach threshold. And so now you can see that the activation gate is completely open. The inactivation gate has been open this entire time, and so we have a pore that's created through the membrane for sodium. This is the open or active state, and it allows sodium ions to enter the cell and bring their positive charge with them, and that's what causes that depolarization phase of the action potential. To tie this back to the previous unit, the increase in sodium permeability moves membrane potential from rest towards sodium's very positive equilibrium potential. Now, sodium ions will continue to enter the cell until membrane potential reaches around positive 30 millivolts. At this point, the inactivation gate closes, and this decreases the sodium permeability to about 0. This causes the action potential to peak, and it causes it to begin to repolarize. To tie this back to our previous unit, we could say that decreasing sodium permeability causes membrane potential to move away from sodium's equilibrium potential. Now, there's two important points that I want to make here. The first is that the inactivation gate is not really voltage sensitive. It's a stochastic or probabilistic process, similar to flipping a coin. When the voltage-gated sodium channels are open for a long period of time, the probability of the inactivation gate closing increases. Secondly, if you take a closer look at the cartoon up at the top, you can hopefully see what this inactivation state really is. Because if you look closely, you can see that even though the inactivation gate is closed, the activation gate is still open. So the channel is anatomically different here than what we saw in the previous pictures where we were in either the open or the closed state. So the reason that the activation gate is still open is because membrane potential is still above threshold. And in fact, that activation gate is going to stay open until membrane potential goes back down below threshold, closer to rest. So thinking about this whole system, you might notice that it sounds a little bit like a positive feedback loop, and it is. In fact, it might be the only positive feedback loop that we talk about in this half of the course. In other words, I just described a system to you where depolarization opens a channel that causes more depolarization. And that depolarization can open nearby voltage-gated sodium channels, bring them to threshold, and that allows more sodium ions to come into the cell and more depolarization to occur. So this creates amplification. It's the reason why the rising phase of the action potential can happen so quickly. It has such a steep slope to it. The inactivation gate, which isn't voltage sensitive, serves as the outside factor that turns the system off. Now, decreasing the sodium permeability is enough to repolarize membrane potential. But in order to speed up this process of repolarization, we can enlist the help of voltage-gated potassium channels. That is, channels that are selective for potassium ions that are also opened and closed by changes in membrane potential. These are also found all along the axon hillock and the axon. And they're just as complicated as the voltage-gated sodium channels, but I'm not really going to talk about them in the same level of detail. And this is because I think we can appreciate the concept from talking about the sodium channels instead. So I always feel like if we were to talk about the potassium channels in the same amount of detail, I would just be giving you more to memorize without really adding anything additional to conceptually understand. So the important thing to mention is that the voltage-gated potassium channels open more slowly than the voltage-gated sodium channels, and they also reach their peak permeability during repolarization phases of the action potential. Now, if you go back to the permeability graph that I showed you just a couple of slides ago, you can see this a little bit more clearly. But the other key difference that I want to make is that the potassium is at a different concentration gradient. So it's higher inside the cell. And that means when potassium channels are open, potassium ions actually leave the cell and they carry the positive charge out of the cell. And that leads to the development of a negative potential inside the cell at the membrane. In other words, an increase in potassium permeability pulls membrane potential towards potassium's really negative equilibrium potential.